In this video, we're going to develop some of the general results about projectiles. So we're going to be firing a projectile from ground level with speed u at an angle of theta to the horizontal. And that means that we can write the initial velocity as being little u cos theta in the x direction and little u sine theta in the y direction. Now notice that we've also said that we're going to have capital U being the component of the initial velocity in the x direction and capital V as being the component of the initial velocity in the y direction. In other words, we've got capital U is equal to little u cos theta and capital V is equal to little u sine theta. The constant acceleration equations give us the velocity v and the displacement r at any subsequent time. So we've got the equation v equals u plus at, which means that the velocity at any time has a component of u in the x direction and it has a component of v minus gt in the y direction. As before, remember that this means that the horizontal component of the velocity is constant throughout the motion. That's not a surprise because the acceleration is acting downwards only. And the displacement equation we've got is r equals ut plus a half at squared, which gives me x equals u times t, and the y coordinate at any point during the motion is equal to v times t minus a half gt squared. From the equations that we've got here for v and for r, we can make several deductions. The first one is for the time in flight, which we're going to call capital T. Now at time t, the projectile is about to hit the ground, so the value of y must be equal to 0 when little t is equal to capital T. And if y is equal to 0, that is telling me that v times capital T minus a half gt squared must equal 0. Common factor of t, so I've got t times v minus a half gt must equal 0. So either t equals 0, which is not particularly interesting because that's the initial time, so that's the point where we are projecting the projectile, or we have got v equals a half gt. In other words, t must be equal to 2v divided by g. So we've got the time in flight is 2v divided by g. If we remember that capital V is the same thing as u sine theta, then we've got capital T is equal to 2u sine theta divided by g. From this, it is nice and easy to deduce the range of the projectile. Because when t is equal to capital T, the x value is going to equal the range of the projectile. We know that the projectile hits the ground when t equals 2v over g. We know that x is equal to u times t. So therefore we've got the range is x is equal to u times capital T. In other words, that's 2uv divided by g. But we know that capital U is the same thing as little u cos theta. We know that capital V is the same thing as little u sine theta. So we've now got the range can be written as 2u squared sine theta cos theta divided by g. And if we recall the fact that sine 2 theta is exactly the same thing as 2 sine theta cos theta, then we can see that we can write the range as being equal to u squared sine 2 theta divided by g. The biggest possible value that sine 2 theta can take is 1. And it will take that value when theta is 45 degrees. So you can say that the biggest possible value for the range is u squared over g, and that occurs if we have an angle of projection of 45 degrees. We can also work out what the maximum height of the projectile is, and we're going to call that capital H. At the maximum height, the particle is travelling horizontally, so the y component of the velocity must be equal to 0. Well, we know the y component of the velocity is given by v minus capital V minus g times t. So we've got capital V minus g times t must equal 0. In other words, t must be equal to v divided by g. When t is equal to v over g, then the y coordinate is the value of h, but we know the y coordinate is equal to vt minus a half gt squared, so in this case that is v times by v over g minus a half g times by v over g squared. Now looking at that expression there, what we've got is we've got v squared over g minus v squared over 2g, which simplifies to v squared over 2g. So we've got the maximum height is v squared over 2g, which can be written as little u squared sine squared theta over 2g. So we've got the maximum height is v squared over 2g, or u squared sine squared theta over 2g. Finally, we can work out the equation of the path. Now looking at the displacement equation, we know that x is equal to u times t. That's capital U times t. So t is the same thing as x divided by capital U. We also know that y is capital V times t minus a half gt squared. And if we substitute for t, that gives me y is v times x over u minus a half g times x over u squared, which simplifies to y equals v over u times by x minus g over 2u squared times by x squared. So it's certainly the equation of a inverted parabola. Now, capital V divided by capital U is the same thing as little u sine theta divided by little u cos theta. So that simplifies to tan theta. And g over 2u squared is the same thing as g over 2 times by little u squared cos squared theta. So we can rewrite the equation of the parabola as y equals x tan theta minus g over 2 u squared cos squared theta, lots of x squared. Now, we do need to be aware of the modelling assumptions that are made throughout our projectile work. We're treating the object as a particle, we're ignoring air resistance, and we are assuming the acceleration due to gravity is constant. The value of g does vary slightly over the Earth's surface. The value of g at the poles is not the same as the value of g at the equator. As the object moves away from the Earth's surface, then the acceleration due to gravity decreases. But the assumption of constant g is reasonable as long as the object's maximum height does not exceed 10 kilometers. Any of the results that we've established in this video, you might be asked to prove as part of a question. However, you should not use these results without proving them. So if the question doesn't ask you to prove them, you shouldn't quote them. Instead, you should start with the basic constant acceleration equations that we've been doing all of the time, namely v equals u plus at and r equals ut plus a half at squared. So that concludes our series of 3 videos in which we look at the motion of a projectile.